In the last video, we talked about linear independence briefly, and we said that in order for a vector set to span R2, we needed two of those vectors. They needed to be linearly independent, and they needed to be in R2. Both of them needed to lie in R2. And then we said that in contrast, in order for a set of vectors to span R3, we needed to have three of them. They needed to be linearly independent, and they needed to lie in R3. We could extrapolate that now and say that in order for a vector set to span any space, we'll call it Rn, we need to have n vectors, they need to be linearly independent, and they need to lie in Rn space. In this video, we really want to focus on R2. We really want to focus on the set of vectors that spans R2. And so we're going to go through each of these conditions. And the first one is that we have to have exactly two vectors in order to span R2. Remember before that we sort of had this visual idea where if we have the R2 plane here, so let's just say this is the first quadrant in R2, we have X and Y. And let's say we have here 1, 2, and 3, and then 1 and 2. So if we have a vector, we'll sketch it in standard position and we'll call it the vector 2, 2. So it comes up to right about here. So let's call this vector V, and it's the vector 2, 2. Well, if we just take linear combinations of that single vector, those linear combinations are just going to look like this. We'll multiply by some constant coefficient, C1, the column vector 2, 2. This is all we can do with one single vector in terms of linear combinations of that vector. So in other words, if we only have one vector, all we can do is multiply it by some constant scalar. And no matter what I multiply by, I'm still going to end up somewhere along this line. And I might be down here in the third quadrant, but either way, I'm going to end up somewhere along this line. So the single vector can't span R2 because no matter what linear combination I take of this vector V, I'll only end up somewhere along the line. And so if I want to get to this particular point here, 3, 0, I'm not going to be able to it. I'm only going to be able to reach points along the line. If I have two vectors though, let's say I have the vector V is 2, 2, and let's say I also have the vector W, which is the vector 4, 4. Now I have two vectors, which I'm saying here might be able to span R2, but the problem is they're not linearly independent. The vector 4, 4, if I sketch it in standard position, lies right along the same line as this vector 2, 2. They're parallel to each other. And the reason I know that, even if I don't sketch out these vectors on the graph, I know that because W is just a scalar multiple of the vector V. If I multiply V by 2, I'm going to say 2V is equal to 2 times the column vector 2, 2. And the result here, when I distribute the 2, is the vector 4, 4. And that's the vector W that I'm saying I have. So really, 2V is equal to W. And because V and W can be written as linear combinations of one another, I could also divide both sides by 2 and say that V is equal to 1/2 times the vector W. So in other words, because I can write V and W in terms of each other, they are not linearly independent, they are linearly dependent. In order to span R2, I need to come up with two different vectors that cannot be written in terms of each other. We can't write an equation like this one, where we just scale one up by 2 or scale one down by 1/2 and have an equation that shows how we can define one vector in terms of the other. As an example, if I have two vectors, let's say I have the vector 1, 1, and I have the vector 0, 6, there's no way that I can express these two vectors in an equation like this one. Because in order to get from 1 to 0, I would have to multiply by 0. But if I do that, I'm going to get 0 here in the second position. I would get 0, 0. So if I multiply this vector by 0, I'm going to get 0, 0, which gives me this component, but not the 6. If I multiply this vector by 6, I'm going to end up with 6, 6, which gives me the second component here, but not the first one. So there's no scalar that I can multiply by 1, 1 in order to get me to 0, 6. And there's no scalar I can multiply by 0, 6 in order to get me to 1, 1. So these vectors, because of that fact, are linearly independent. So how do we actually test for linear independence? Here we looked at sketching out the vectors and kind of determining visually. Here we set up an equation and we were just able to see easily that we could multiply by the scalar of 2 to get to 4, 4. And here we kind of ran a quick test where we multiplied the 1, 1 by 0 and by 6 and realized we couldn't get here. But these are all kind of just different hacks for figuring out linear independence or linear dependence. So what's the actual method that we can use to test this every time where we don't have to sort of rely on our intuition? That method is to set up an equation. So what we do is we take a set of vectors like this one, we multiply each one by a scalar. So we'll multiply 1, 1, we'll take this example, we already know it's linearly independent. So we'll multiply 1, 1 by the scalar c sub 1, and then we'll add to that c2 times the vector 0, 6, and we'll set that, and here's the key, we'll set that equal to the 0 vector. This is your test for linear independence that's going to work every time. If the only possible solution for C1 and C2 are 0 and 0, in other words, if the only way to make this equation true is if the values of C1 and C2 are both 0, then I know my vectors are linearly independent. If I can find some other combination of C1 and C2 that makes the equation true, then I know my vectors are linearly dependent. So let's solve this one. What you do is you break up this vector equation into a system of two equations. So you say C sub 1 times 1 gives you C sub 1, plus C sub 2 times 0 gives you 0 is equal to 0. You just work your way across the top. The result here you see is C sub 1 equals 0. Then we work our way across the bottom. We say C sub 1 times 1 plus C sub 2 times 6, so 6 C sub 2 is equal to 0. Well, in this equation, we can make a substitution. We already found C sub 1 is 0, so we'll substitute in and get 0 plus 6 C sub 2 is 0. That gives us 6 C sub 2 is 0. We divide both sides by 6, and we get C sub 2 equals 0. So the only values for C sub 1 and C sub 2 that make this equation true are 0 and 0, and so that tells you that these two vectors are linearly independent. On the other hand, let's prove that this method works for our vectors here, v and w, 2, 2, and 4, 4. If we set up the same equation, C sub 1 times 2, 2, plus C sub 2 times 4, 4, and we set that equal to the 0 vector, we can break it into a system of equations and solve those for C sub 1 and C sub 2. So working our way across the top, we get 2 C sub 1 plus 4 C sub 2 is equal to 0. And then working our way across the bottom, we get C sub 1 times 2, 2 C sub 1, C sub 2 times 4, so plus 4 C sub 2 is equal to 0. So I have the same equation in both instances. If I solve one of these, what do I end up with here? I'll divide both sides by 2, and I'll get C sub 1 plus 2 C sub 2 is equal to 0. If I subtract 2 C sub 2 from both sides, I'll get C sub 1 is equal to negative 2 C sub 2. And as you can see here, I can come up with loads of combinations that are going to make this equation true. For instance, if I say that C sub 2 is equal to 1, that tells me that C sub 1 is going to be equal to negative 2. If I say that C sub 2 is equal to 2, that tells me that C sub 1 is going to be equal to negative 4. So I'm coming up with all these combinations that are not 0, 0. I have negative 2, 1, and negative 4, 2, and I could come up with infinitely more solutions that are not 0, 0. So because I can find a solution, and I only need one, but because I can find a solution that is not 0, 0, that tells me that these two vectors, 2, 2, and 4, 4, are linearly dependent. So we've shown here that one single vector will never span R2. We've shown that two vectors can span R2 as long as they are linearly independent, and we've shown how to determine whether a set of two vectors is linearly independent. The only other point we want to make is that any more than two vectors will never be linearly independent. So one vector won't span R2, two vectors will span R2, three vectors will span R2, but one of them will be redundant or unnecessary, making the set of three vectors linearly dependent. And that's because if I can already span R2 using any combination of two linearly independent vectors, then adding a third vector to that is never going to give us any new information. I can already get to every point in R2, every point in the two-dimensional space, using just two vectors. So adding a third vector doesn't get me anywhere new. And we can really prove that to ourselves with this same test here. Let's say I pick a random vector, we'll call it 2, 3. I can set up the same equation here. So I can say c sub 1 times 1, 1 plus c sub 2 times 0, 6 plus c sub 3 times, what do we say, 2, 3 is the vector? It doesn't matter. They're always going to be linearly dependent. And we set that equal to the 0 vector. If I break this apart into a system of equations, I'm going to get c sub 1 plus 2c sub 3 is equal to 0. And then I'm going to get c sub 1 plus 6c sub 2 plus 3c sub 3 is equal to 0. And we can see the same thing work itself out. We're going to be able to find at least one solution to this that is not c sub 1, c sub 2, and c sub 3 all equal to 0. If I take these equations and I solve both of them for c sub 1, I'm going to get c sub 1 is equal to negative 2c sub 3, and I'm going to get c sub 1 is equal to negative 6c sub 2 minus 3c sub 3. Because they're both equal to c sub 1, I'm going to be able to set them equal to each other and get negative 6c sub 2 minus 3c sub 3 is equal to negative 2c sub 3. And then if I add 3c sub 3 to both sides, I'm going to get negative 6c sub 2 is equal to negative 2 plus 3 is a positive 1, so positive 1c sub 3. And this equation right here shows why these three vectors are linearly dependent. If I start picking values for c sub 2 in this equation, let's say I choose that c sub 2 will be 1, then I can see that c sub 3 will be negative 6. Or if I choose c sub 2 to be positive 2, I can see that c sub 3 will be negative 12. And when I take those values for c sub 2 and c sub 3 and plug them back into either of these equations to find c sub 1, even if c sub 1 came out to be a 0 value, we've just shown that there are values for c sub 2 and c sub 3 that can be non-zero. And this is always going to be the case. Any set of more than two vectors in R2 is going to be linearly dependent because one of them is going to be unnecessary. So that's the idea of linear independence and span in R2. And then in the next video, we'll talk about linear independence in R3.